to set a problem up, what we have to do is we have several config files. You'll see in here we have the step 01, step 02, step 03, and 4. And then we also have the PyLithApp.config file. And so that's the first one we're going to look at, because that one has parameters that are common to all of the simulations that we're doing. And then with these other ones, we just either override or supplement whatever's in the PyLithApp config. So, well, how different is it? Is it different?
So all your apropos commands, we have an asterisk, we have the dollar sign in front now.
Ah, I forgot. Okay. Well,
Charles is using a slightly different branch that was a little slightly out of date. We have an apropos command showed where we had a the comment character. You can either use the comment character or you can use the dollar sign. I've switched everything yesterday or Saturday to the dollar sign.
Oh, wait.
To make it different.
All right. Okay. Let me see. So if I look at the...
So if he switches to master, you'll see exactly what... You'll have the same files that he has. Okay, well, maybe it's the main branch.
So was that always there?
Yeah, it was always there, and we didn't realize it until we were proving the documentation on Sunday that you could differentiate between comments and apropos commands. So we decided it would be clearer in the scripts that they don't use the comment character to start with apropos. There's all sorts of stuff in the documentation. So if you see good things like that, be sure to pass them on.
Okay. Anyway, this is our PyLithApp.config file, and so, like I said, this has things that all of the different simulations in this directory are going to use, or we may change them. For instance, we may change the total time rather than 200 years. It may be either 0 years, 300, whatever, but they can be changed. These just how talkative you want PyLith to be. And so we have it, you can turn on journaling information for all these different aspects of it, the time-dependent formulation, implicit PET-C information, the linear solver information, meshing stuff. There are a lot of different ones you can turn on. You usually kind of like just what's going on, because for one thing, if you have a problem that you can't fix, we'll want the log file. And if you don't have this, then we can't see anything. So the first thing we're telling it is that the mesh generator, we're using qubit mesh, which is what we'll be using for almost pretty much everything. Then we actually down here, you'll notice it's hierarchical. So we have PyLithApp. This is what Brad was showing, the kind of the way you have facilities and then, or facilities and properties. So this is the facility and then the properties within here. Our problem down here is two-dimensional. Then we have, right now, we're giving it a simulation time of 200 years and a time step size of 1 year, but we might change that for some of the simulations. We have 4 materials. So the materials we set to an array, and these are names that we just give it here, continent, crust. But then down here, we have to actually, first we have to say what kind of material each one is going to be. So that's what we're doing here. So we're saying continent crust is an elastic plane strain material. Ocean crust is also that. And then the 2 mantle materials are Maxwell plane strain materials. Then we come down. That's general information for all of the materials. Now for each separate one, the continental crust, we give it a label. This is useful when you're running the code. You like to be able to see what material you're working on. This ID number here if you look, remember from when we were using trellis, we had a block 1, and that was the continental crust. So this ID number corresponds to that block number. And then we're going to have a database of properties. And so that database also needs a label. And we'll just say continental crust properties. And then we're going to give it a file name where it gets those properties. And we'll look at one of these in a minute. These are spatial database files. So this is a file that's also, it's over here. And so, and then we have to tell it what sort of quadrature. A triangle is a simplex type of cell. If we were using quadrilaterals, it would be Lagrange. It would be Fiat Lagrange. But in either case, our cell dimension would be 2 because this is a 2-dimensional problem. Same thing for all of our other materials. This is our continental mantle, so really the only thing different here, other than the labels and the ID number, is the spatial database where it gets its information. We have a particular database for that. This part is the same. It's also a Fiat simplex element, dimension of 2, and then the same for the oceanic material. Then the final thing we're going to do in PyLithTutorial, nope, not the final, next thing, is we're going to about the type of output. We're not going to provide specifics, but we're going to say, for instance, for our solution, we want 2 different types of output. The solution can be displacements and velocities if you have a time-dependent problem. So we want to first output the displacements over the entire domain output type, but we also want to output it over a subdomain. And in this case, we're going to define the subdomain to correspond to the upper surface of the mesh. That's a lot of times for problems that we're interested in. We want to know what's going on the upper surface because that's what we see. So, so in that case, we have to tell it what we're setting the subdomain, the type of component as an output solution subset. And then down here, we'll tell it which subset to use. So we'll output a subdomain that has the label ground surf. And that was one of our node sets that we defined in Trellis. So this tells PyLith that for that node set, we'll output the solution corresponding to that. Then for each type of output, we'll give it an output frequency. For the entire domain, we're just going to output it every 10 years. We're going to use HDF5 output, which, as Brad was explaining, is a lot faster and easier to work with. And then we do the same thing here. For the ground surface, we're also going to have HDF5 output. And then we have our material output. So we have to have a separate output for each material type. So we have one for our continental crust. The first thing we do, it's not important for triangles because there's only a single integration point. But for some of our element types, there's multiple integration points within an element. And if you were to output all of that, visualization packages usually have no idea what to do with that. So we have different filters, and we can filter everything so it averages over an element to a single point. Then when you're visualizing, ParaView, for instance, would know to apply that the values within that, just within that cell. So we that's the cell filter average. We average all of the integration points over a cell and then put them to a single point. The output frequency, we're saying do it by time step, and the time step size is 10 years, and again, we're doing HDF5 output. So we do this for each of the different material types. Let's see. Okay, I guess we're not defining it for the faults in here. We'll do that separately in the separate config files. And then the last thing we have are our PET-C solver options. And I believe Matt is going to go into more detail about those tomorrow. But typically, ASM is kind of our standard solver option. It's not maybe the most efficient, but it's pretty robust. And then these are kind of standard tolerance. This is your KSP convergence tolerances. So there's a relative tolerance.
It's the linear.
Yeah, linear solve. Yeah, linear solve. So relative tolerance, absolute tolerance, the maximum number of iterations for the linear solution, and then this restart option. And I'll let Matt go through all that later. Yes.
Because of round off there, if you say, if you say 10 years, there's round off there. And so if you want every like 10th time step, it may end up skipping and giving you 10 years plus however many time steps.
The reason is because PyLith will grab the most recent time step.
PyLith will wait that long between it for it to act. And so there are round off, you're asking, it's doing a precision calculation that is comparing two floating point numbers to be is have I weighted greater than or equal to the time since you requested time step. If you say 10, things can get it's not when in double precision it doesn't store necessarily 10, it stores a value that's close to 10 given the number of bits of precision it has.
There is another option.
This is the easiest way to make sure that if you want 10 years, you give it epsilon less, where epsilon is the precision of the computer you're running on.
Yeah. Well, that's true. If you have a constant time step size, there is an option to just skip so many time steps for output. So that's another, but this is a pretty simple problem, but for a lot of problems, you're not going to have a constant time step size. So we told it what the time step size is. We're saying it's 1 year, but yeah, to do with the solution, yeah. So anyway, so these are, we have your preconditioners set up, your convergence parameters, and then this is just the information that you get from PET-C as you're doing a linear solution. We want it to monitor the solution because we want to know what the convergence is looking like. We want to view the solution. We want it to tell us whether or not it converged. These are not pertinent to what we're going through today because that's for the nonlinear problem. We're just going to do a linear problem today, so I'll leave that for later. So that is the information that's common to all of the simulations. And I believe, let's see, I think I'll show you next. Wait, no spatial database? Yes, we do. I'll show you one of these spatial databases here, just to see. Yes.
I had some older files, and I noticed it says PyLith.problem.
Oh, you can. Time dependent is a type of problem, so you can use either one. It's more general to say, but
there's a Green's function problem.
Yes.
So if you want the same parameters to work in the Green's function PyLith app, you'll see we use problem in our PyLith app because we want that same for both a Green function problem and a time dependent problem.
Yeah, because so we have problem, we have time dependent, we have Green's function, and so this, so the way it's set up, you can tell it. And I've gotten used to using problem now because I'm playing with Green's functions a lot, and so I want it to work for either one. So But if you try and say time dependent and you're generating Green's functions, you'll have an error if you try and give it those values to a Green's functions problem. Yes.
Is there any documents that I can check and define how to set up this mechanism?
Well, in the manual, it's pretty detailed, I think.
We'll go over that tomorrow in the debugging session where you can ask for what are all the parameters being set, what are the parameters for a given object, what are the options, what is being used for that parameter, and when you get an error message, some of the error messages will say, time dependent or problem, and to help guide you. So it's covered quite a bit in the manual in terms of what is being used and what's available, but in the debugging session, that's one of the things we want to do is try and get people to understand sort of how to decipher things like this and where to look up that various information.
Okay.
So I think maybe our break, there's food outside, so how about we take a 10-minute break right now?
Okay.
And then come back so that we don't have a break right before lunch.
All right.
No, but I mean, it doesn't go. Because it's just, even if it was on the beginning,
So did you run it?
it works, you know? So, yeah, okay.
Okay. Is it?
So it needs to, the load I put in needs to vary smoothly or something like that.
Well, the thing is, even in tech time, you apply a point, and in reality, it's not a point. It's
It's over that.
Yeah, it's over that. And so it's kind of I don't think there's a problem doing points, but
Yeah. There's no advantage
yeah, I'm trying to.
in terms of basis.
Yeah, I don't think there is because
I don't know.
you could create a traction that looked the same.
Yeah. Right.
Yeah.
I didn't know. So Brad, I guess my real question is, why don't the
Spatial database?
No, so with regard to a loading problem, why do I need the spherical basis functions when I have a complex load versus what you're planning on adding?
So your complex load, you had points where you had like fine space here and very coarse here. And it's when points are relatively uniformly distributed.
Right, which is not. Yeah.
Which things work well. If you need when you go coarse and fine, it has problems because it only looks at the nearest so many points.
So this is what I was saying, that the level of description that's breaking down is not the pilot level, it's the spatial database level. The spatial database is not forming a faithful representation of your complicated
Right.
load.
Right.
So
it
if
doesn't
you have a
do
smooth-
it even with a single load.
That's well, then
It looks. If I do a linear the linear will look right.
But you have a 3D.
No, this is just a one load. This is a single load.
What do you mean? How many points?
1 point. One traction over one central cell. That's what added the complexity, but even with a single cell, it doesn't look right.
It's doing what
Oh, well, they'll get some interesting. Can you edit them?
I finally converted my wife to doing everything on the lab. What I find is if you like then it all becomes that.
Testing. Does that work? Maybe it should be down there. Is that all right? Okay. Okay. After a very short break, my goal, I guess, is to finish in the next 8 minutes. Anyway, this is in the PyLithTutorial.config file we just saw. It referenced spatial databases for each of the different materials. And for this problem, we've chosen the simplest type of spatial database you can have, which is just what we call a zero-dimensional. That means uniform properties throughout the entire domain. So this is the one for the, let's see, which one is this? This is the continental mantle. And so what we give it here, we have just kind of a standard format, very simple ASCII format. It's a simple DB. It has 4 values, and those are density, BS, BP, and viscosity. And then we give the units for each of these values. So we have kilograms per cubic meter, meters per second, and then Pascal seconds for viscosity. And then we just have one location. Since this is a 0D spatial database, that's all we need, because one location is for the whole domain. So since that's true, our data dimension is 0. If we had 2 points, like to specify a variation along the line, that would be 1D. If we had variation along the surface, that would be 2D. And then if we had variation throughout the entire volume, that's a 3D one. So this is the simplest kind you can do. Spatial dimension is still just 2. We're using a Cartesian coordinate system. We don't really care about what this is since it's just a single point, but in many cases, like if you wanted to give your coordinates in kilometers, you could put a conversion factor here, what you would need to convert the coordinate values to meters. And again, for our coordinate system, the spatial dimension is also 2. Now, this is kind of like a header that describes the spatial database, and then all you have to do is give, since this is 2D, just x, y coordinates, and then the values for our different properties. So here's our density, Vs, Vp, and then we're giving a viscosity here. And so apparently this is going to give us a relaxation time of 200 years, which is just up here, viscosity over the shear modulus. So there's a simple spatial database, and now for our now we're going to look at the config file for step 01. And okay, so these are values that are specific for our first example, which is just coseismic slip. So we've changed the total time to 1 year, since this is just a static, or to 0 years, static solution. And we have our boundary conditions here. We have an array of 4 boundary conditions: our east crust, east mantle, the western boundary, and then the bottom boundary. And so for each of these, we're using the default zero displacement boundary condition. Each one, for instance, the east crust, we tell it which degree of freedom we want to constrain. That's what we're doing right here. And this degree of freedom, 0, corresponds to our x coordinates. So that means that for the eastern crust boundary, we're constraining it in the direction normal to the boundary. We're going to do that for all of them. We give it a label. Almost sneeze. And then we give the database a label as well. And okay, then we do the same thing for the mantle part of the eastern boundary. 0 displacement, constrained in the x direction. And then for the western boundary, same thing, constrained in the x direction. And then finally, the bottom boundary, we're constraining in the y direction, since that's normal to the boundary. Okay, then the faults, we're going to have an array of a single fault. So our interfaces is just a single fault. And then we set the type of fault. This is fault cohesive kinetic, which means that we're specifying the slip on the fault rather than having a dynamic fault. And then we come down and we give it the node set for the fault. So the label fault slab top, that is one that we defined as a node set in cubic. And then we're going to come down and define the time at which slip occurs and the slip distribution. And so that's what we're doing down here. We have rupture slip function, and then we have a file name associated with that, which is fault slip coseismic.spatialdb, and we can look at that. We're going to have it interpolate linearly for this spatial database. The default is nearest neighbor, but you can have it do linear interpolation instead. And then finally, we're going to give this a label, just call it final slip. And then the slip time is just, you can have different times for when slip occurs. So we're just going to do that right here rather than using a spatial database. We'll just tell it right here. So we're going to use a uniform DB rather than a simple read. We're going to give it a label of slip time. We're going to tell it the values. It's just a single value that we need to provide, and that's slip time. And then we're going to have it slip at t equals 0 years, since this is just coseismic dislocation. And then finally, we provide some output file names. So these are specific for this section. So for the entire domain, it'll just have, we're going to put in the directory output. We'll have a file called step01.h5. Similarly, for the subdomain, we're going to output the solution at the ground surface. So we'll call that step01-groundsurf.h5. And then we'll have output for the fault. So we'll give that a similar type of name. And then for each of the materials, we'll give them each of them a name that's specific to the material that it corresponds to. So really, we haven't done a lot here other than we've provided the boundary conditions, we've told it about the fault, and we're referencing this fault slip spatial database. So we can just look very quickly at that, unless you think we should just run the simulation.
No, let's look at that.
All right.
It's not a single point.
Yeah, so that's why we would look at it.
I think we should skip a step.
Okay, so we'll just do co-seismic. Okay, so here's our spatial database. And so it's similar to the top part. We have two values in this case, left lateral slip and fault opening. Okay, for a 2D problem, left lateral slip is kind of subjective. It's just because since there's only 2D, we don't have up-dip slip, but you can just use it just the same. And so we're going to specify our slip in centimeters. We're going to have 17 points that define our slip distribution. So that means our data dimension is 1 because we're varying these values along the line. So spatial dimension is still 2, still a Cartesian coordinate system. In this case, we're going to specify our coordinates in kilometers. So we're giving it a conversion factor here. And again, our coordinate system has a spatial dimension of 2. So this is just a point that's up above the mesh, just so that when we do a linear interpolation, you bounded your domain there. And so so we have a point that's 99 kilometers up in the air. And then from there to 0, we have no slip at all. And then starting at 7 kilometers, 7.5 kilometers depth, we start having slip. And then it increases to maximum value right there. And then we taper it down. And then by 55 kilometers depth, we've gone back to 0 slip. And then this is a point way down below the bottom of the mesh, just to make sure we can interpolate.
An important thing to point out is notice that things are just as a function of depth. X is equal to 0 in all the cases. So this is an advantage of using a spatial database in that we've just given us something as a function of depth. We haven't said what the X, Y coordinates of the fault are. So this makes it a lot easier. Someone gave us a depth variation of slip with depth, maybe using a different coordinate system like latitude, longitude, and we've taken that to our, it's independent of our discretization size, independent of our cell size, independent of the geometry of our fault. All we have is a function of depth.
Yes. And then in our config file, we told it to do a linear interpolation. So we'll get a nice, pretty decent representation of this fault slip. So, okay, yes.
Is there any particular reason why the slip is specified in centimeters?
Just whatever you want.
So you can do it.
Yeah, it's just to show the importance of this up here. That, yeah, it's a demonstration. Yeah. Most earthquakes will thing, but not
No,
this one. Yeah.
Because it will be non-dimensionalized.
Yeah.
So it won't matter what you type in as long as you have a reasonable size for non-dimensionalization.
Is it necessary to put in the 99 kilometers?
Well, the reason is because it's again a possibility of round off. Well, actually, we have topography and bathymetry, so we want to make sure that you're never trying to interpolate outside of where you provided values, because then it blows up. So
You'll get an error.
yeah, you'll get an error. Yes. So it'll say unable to interpolate to a point at, and it'll give you the coordinates. And so, yeah, that's just to make sure that that doesn't happen. Okay, so now we can go ahead and just run it. So yeah, like Brad said, yeah. Yeah, it only cares what the y-coordinate is in this. Well, okay.
So the difference between setting a slip exactly on the fault and setting it here is when you do the linear interpolation, the weighting factor is just going to depend on depth. It won't depend on the true length along the fault. So if you actually specify points along the fault, the interpolation will look slightly different, but not a lot different. And most of the data they have is only by depth. It's not very exact. So this is probably the right interpretation.
So your points will be projected onto this, and so these points are not projected to your geometry. Your geometry of wherever you are in space is projected to this line. So you can make your line. You could do something horizontally at the ground surface in that view. The same way, you'd say, you know, along strike, I have this variation in slip, but there's no variation in depth.
Yeah.
It says, you told me this is a one-dimensional, so I'm going to find it does it automatically. It says, okay, I have these 2 points, these are the nearest 2 points, I'm projecting your point onto that line.
So it's a
No, well, it doesn't know it's 1D in depth. It figures out itself that you have specified, you know, where these lines are in 3D space. You can give it horizontal, vertical, or somewhere in between, and it'll find out what line
it's a least squares fit to this data. You would assume specify some size and then do a least squares fit of the dimension. So if it's to a plane through this, and then take the orthogonal projection on the dimensional manifold. So if I specify points in the spatial database that weren't on a line, I said that it would be least squares.
No, not that smart.
Yeah, because you have a least square set to 2 points is just exact.
If you have a sequence of points for each 2 points.
It'll look at the nearest point that it can find to do the interpolation, and it'll project onto that line.
So that's two point least squares. You could expand it to that.
Well, yeah, in 3D, I mean, if it were a slip distribution, you probably want a variation over a surface.
So I can write down the least squares problem, and it would make sense. The thing is whether what you're telling me is totally determined. If it's underdetermined,
yeah. Rowena, did you still have? No? Okay. Okay, so. And so the one thing that I'm doing here, I'm redirecting output to a log file because we almost always want to do that just so we can see what happened when we ran it. So by default, PyLith will read the pylith.config file, but then we provide any additional configuration files we want it to use. So that's the step01.config file. So we're saying pylith step01.config. We're redirecting output to this log file, and we'll just run it. Oh, if we wanted to run it on more than one processor, we could, we can just do that for fun. Then you could just do that here. You can tell it how many nodes to run on. So I'll just run it. And there we go. The reason you do a log file is because it just spews all this stuff out, and you're not going to be able to read it while it's going. So, but we can look at it. And this is a result of all the journaling information we set up. We have it reading the mesh, it's reading our node sets. It goes on, it tells us some of the shape function, basis function information. A lot of times you don't need to know this, but sometimes it's handy. It'll go through all of this, the different parts of the solution, setting up the boundary conditions, and then initializing the problem. So it initializes all the different parts of it, starts setting constraints, and then finally we get down to the part where we integrate the residual and we solve our equations here. And this is information from PET-C. So this is the linear solution process. It's just showing how our residual norm is decreasing with the number of iterations. Actually, a fair number there, but yeah, ASM. Okay, and then this is where we told it to tell us, you know, that it converged. If it didn't, it would have told us that. And then you'll probably cover all this kind of stuff, right? So I don't think that's just a lot of stuff. And what we didn't do the log summary, which is another thing that you frequently use. PET-C will give you all sorts of information about how much time each particular little part of the code took to run and things like that. So now that we've done all